something that's a property. Is that working now?
Yeah.
Okay. So a property of the covariant derivative that we call is the following. Basically, the covariant derivative of the metric itself vanishes. Okay, this is always zero. This property, we say that the covariant derivative is compatible or associated with the metric. Okay, or associated. Okay, and this is just a little PS. For yesterday's lecture, you can add that in the section where we discussed the covariant derivative. Okay. So now, are we complete now?
Yeah.
Okay, great. Then, so let's start with the next part. So we said we're talking about the 3 + 1 decomposition. I introduced the normal vector yesterday. And there was a question about the direction of the normal vector. And as I was going through it, I realized that I believe it's another thing we need to clean up. I think there was an epsilon missing in the definition. Okay, so basically, let's just collect what we had. I wrote down the normal vector, and it should be minus epsilon alpha g a b nabla bt, and epsilon again is +1 if NA is time-like, and epsilon is -1 if NA is space-like. I also told you in the tutorial yesterday that the only reason why I'm introducing the epsilon at all is for this example that we discussed in the tutorial today. We'll get back to that later today. Okay? So for all practical purposes, for the 3 + 1 decomposition in general relativity, you can just set epsilon to 1 and we're done with that. We also introduced the normalization. This is then minus epsilon. Again, for time-like normal vector, this would give us NA, and A equals -1. For space-like, it gives us +1 as it's supposed to be. And then finally, we found from this normalization that alpha equals minus epsilon G AB, then nabla AT, nabla BT, the whole thing to the -1/2. Okay? Now, I think there was one question yesterday about the direction of this. Let's just do this for a space-like normal vector. Okay? If we have a space-like normal vector, then this points in the direction of the greatest increase of t. Then all of this will be positive. The -1 will cancel this -1, and indeed, the normal vector points into the direction of increasing t. Okay, so this is how we want it. All right? Okay, now, what we'll do now with this normal vector is that we'll construct a spatial metric. So we want to construct a metric that is induced on our foliation, right? We introduced this foliation of space-time yesterday. How do we do that? We do it the following way. We say that the space-time metric GAB induces a spatial metric. And how does it do that? We define, this is now where the gamma comes from. Remember the typo in the tutorial. So yes?
Sir, I didn't get the reasoning for why epsilon should be -1 if it is space-like and it is time-like.
Epsilon should be, no, it should be +1 if NA is time-like. Okay?
I didn't get the reasoning behind that. I didn't get the logic.
Okay, just convenience, because basically I'll just introduce the epsilon for today when we talk about general relativity. Actually, okay, today we'll talk mostly about geometry. We'll just talk about the curvature of spaces and foliations and hypersurfaces, okay? When we insert the physics back in to actually get the constraint equations and the evolution equations of Einstein's equations, basically at that point it's really most natural to just choose epsilon equals +1. So you could have chosen, why didn't I do it the other way around, and it would save me the minus, because for all, at some point we'll just want to forget about the epsilon. We'll just set it to 1, and then the minus will be the way that it will be there the way it is supposed to be. Okay? Yeah. We define this as GAB plus, and here's another epsilon, NA, NB. And again, basically, if you look into books on the subject, okay, some of which I'm quite familiar with, then this epsilon won't even be there. That just becomes 1. Okay? Okay, this is now our spatial metric that is induced on our hypersurfaces sigma. All right? So the space-time metric measures proper distances in our space-time. Okay? More generally, we consider this the metric in the embedding space, so that measures proper distances in the embedding space, whereas the induced metric now measures distances only on the hypersurface. Okay? Now, yesterday in the tutorial, we talked about a flat space and spherical polar coordinates. Then we talked about the sphere that is embedded in there. Let's try this out. Okay, let's see what happens if we do it exactly for that case. So let's consider an example. It's the example that we prepared in the tutorial yesterday. And actually we will follow this example today and a bit tomorrow to try out several concepts that we're introducing today. Okay? So we are considering flat space. Okay, in spherical polar coordinates. So that means I have a line element, which is dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Or if I want to, I can write the metric of this embedding space, which I'll use the notation for my space-time metric, right? So the embedding space, GAB, this is 1 r squared sine squared theta, and the rest are zeros, right? Okay. Now we want to consider a hypersurface, basically of the space. And particularly, we want to consider a hypersurface of constant radius r. So that will give us a sphere that is embedded in this space. Okay? So of constant radius r. Now the normal vector on this sphere will be space-like. And that's exactly why I did this little dance with the epsilon, because now we actually need to choose epsilon equals -1. That's the only reason why I'm doing this whole thing. Okay? So actually, let me maybe erase this over here. So NA is space-like. So we want epsilon equals -1. That means, okay. So actually, if you want, we can also draw a little picture. Here's our sphere of radius r, and now actually the first thing we want to construct is the normal vector on the sphere. Okay? So what is NA? Well, NA is, what do we have? Epsilon is -1, so that -1 cancels this -1, so we have just alpha times GAB times the gradient b of r, right? Because r is our function, okay, that defines our hypersurfaces, right? Hypersurface of constant r give us these surfaces. So we want this. But now, basically, there's only one term that enters here, and that is basically the partial derivative with respect to r. So that gives us 1. So we see that basically the only okay, so we only get an r component for this, b equals r, but GRR, even the inverse, will still be 1. So the only component we get here is alpha 0, 0. Right? You're with me? Now we want to normalize this to find alpha. How do we normalize this? What will alpha be? Did I hear 1? That's very reassuring. Okay, so we normalize this. I mean, we could formally insert that into here, and we would find alpha equals 1, right? Basically, we only get the RR component, and we have GRR that is 1. This whole thing is 1. 1 to the -1/2 is still 1, okay? And so this is, we get alpha equals 1. That means that basically the normal vector is just 1, 0, 0, as you might have expected all along, okay? Now, actually, we can also look at the lower index. This will be G, A, B, and B. And of course, this is also 1, 0, 0. Okay? Fine. So now we can construct the induced metric using that normal vector and this metric for the whole space. And then we get G gamma AB equals G AB minus NA NB because the epsilon equals -1. Okay? And what do we get? Well, the only non-zero components here are the R components, but the R components is 1. The RR component of the metric G is 1. So for the R component, we now get a 0. Right? So basically, this metric is, if I write it out, would now be 0 R squared sine squared theta, and the rest are also zeros. Okay? Or if I want to, and now what I notice is that's exactly the metric on a sphere. Okay? So, or if I want, I can also write this as the line element. Now what I'll do is usually I'll use the ds squared as my proper length in the embedding space, and I'll use a dl to distinguish this on the embedded space. So the line element on the sphere is now dl squared. I notice that only these two terms will contribute, and as you might expect, this is r squared d theta squared plus r squared sine squared theta d phi squared. Okay? Now, none of this is particularly earth-shattering or new. Okay? I mean, basically, if I had asked you what is the metric on the sphere, you would have told me this right away. Okay? But basically, this just shows that if we carry through this formalism, that's exactly what you get. This just means, great, we're still on the right path. This is reassuring. Okay? So that's this little example. Now, let's come back to this formal development of our formalism. Yes? Yeah, you know, I have a hard time hearing you. So you're asking about the coordinates on this embedded space? Yes.
Which shows up only on the embedded surface, on the hypersurface, which is not there in the flat space.
Okay, so I'm still not quite sure what. Yes, I mean, basically, I'm getting the coordinates. I basically inherit the coordinates from the embedded space in this case, right?
He's talking about the coordinate singularity at theta equal to 0 and pi.
Oh, okay, of course. But you know, again, so that's a pathology of these particular coordinates. But they already arise in the spherical polar coordinates that I've chosen for the embedded space, right? So if I worry about that, I could choose a different coordinate system, and that would still work. Okay. I mean, here's another comment. Actually, that is good. You give me a chance to say that. The way I'm defining this is all tensorial, right? Basically, I'm defining the induced metric in terms of the space, you know, the embedded metric and normal vectors. All of these are tensors, okay? So all of these expressions are completely coordinate invariant, right? So in particular, that means that if you are worried about these coordinate pathologies on the axis, at the origin, or wherever they may be, then you can always choose a different coordinate system, do this in a different coordinate system. But what you notice from this is the formalism works in any coordinate system. It's coordinate invariant. Okay? Yeah. And I think there was another question somewhere. Did you have a question, sir?
Just there was about the convention. So the fact that you chose LA is space-line versus you would have chose LA is timeline.
Yeah. So I mean that depends on the signature of this space that we're working in. Okay. So in this case, this is a flat space. It's Euclidean geometry, so the normal vector will surely be space-like. Okay. When we get to general relativity, we want to have a time-like normal vector. Okay, because that will be normal on our spatial slices. Okay. Yeah. Okay. Let me erase this. Okay. So we've introduced the spatial metric. Okay. The next thing that I want to highlight is that we can now use that to decompose any space-time tensor into spatial parts and normal parts. Okay, so you think of basically here's our space, maybe this classroom, here's a spatial slice. There will be vectors, maybe this piece of chalk is a vector that points in a certain direction, and now I can decompose this vector into a part that is tangent to the spatial slice and a part that is normal to the slice. How do I do that? Or actually, let me write this down first. We can decompose any tensor into spatial and normal parts. So, for example, here is some vector VA. Now I can write this vector VA certainly as a Dirac delta like this, right? This will be 1 if these two are the same, it's 0 otherwise. So if we sum over this, you believe me that this holds. But the Dirac delta with these mixed indices is the same as the space-time metric with the mixed indices. So you'll believe me that this holds too. Now I can insert our definition for the spatial metric into this, and that will give me gamma AB VB minus our epsilon NA NB VB. Okay? And now we notice that this gives us the spatial part. Okay? This is the projection into the spatial part. This is the projection along the normal. Okay? So this is now a spatial part. Okay? And this is the normal part. And of course, I'm using spatial kind of loosely here, because if we have a spatial normal vector, then you could very well argue about, wait, this part is spatial too. Okay, so really, maybe a better nomenclature would be to use this is the projected part, and this is the normal part. Okay, but I think it's clear from the context what I mean. This is for just one vector. Actually, let's do another example for rank 2 tensor. So let's say I have this rank 2 tensor TAB. What do I do with that one? Well, I do the same thing. I write this as GAC, let's say, GBD TCD. Now I insert the metric, the definition for the spatial metric for the two G's. That gives me two terms. I get a gamma AC minus epsilon NA NC times gamma BD minus epsilon NC ND. Now I multiply this with TCD. And now we notice something interesting. So we're getting various different types of terms. The first term that we're getting is from these two times that one. That will be a gamma AC, gamma BD, TCD, right? And I get an AC, and that's absolutely right. That was a test. I wanted to see whether you're paying attention. No, thanks for pointing that out. Okay, so I'll do many of these tests, okay? Anyway, now the next term, the next type of terms will be those that are mixed, right? So we get a term from this one, and also from this one and that one. So we have a minus epsilon, NA, NC, gamma BD, TCD, minus epsilon NB ND times gamma AC, TCD. And finally, I get a term that are only the normal vectors. Okay, that one will be plus NA, NB, NC, ND, TCD. Okay, so now what we see is that we get all kinds of mixed terms. We have one term that is purely spatial. Then we get two terms that are mixed. And finally, we get one term that is purely normal. Okay? I'm just doing this out by hand in a little bit of detail because in a little while we'll do the same thing for the Riemann tensor. And then we also have to think about these different mixed terms that appear in this decomposition of the Riemann tensor. So this is a little preview of things to come. Okay, okay, that's that. Actually, let me erase this at the same time. Now this operator that we're encountering here, this gamma AB with the mixed indices, that's what we call the projection operator. Okay? So the projection operator. Okay? And so this is gamma AB plus gamma AB, which is GAB plus epsilon NA NB. Okay? And what this operator does is it projects the operator into our slice. Okay? Okay, actually maybe I should write that down. So this projects into the slice, or I could express it, I could say, well, projects it into the plane. Into which plane? Well, into the plane that is normal on our normal vector n. Right? So plane orthogonal or normal. And A. Let's check that. Okay, how can I check that? How does that work? Well, if I contract this normal vector with the normal vector, if I contract the projection operator with the normal vector, what should I get? 0, right? Let's verify that. It's just, a little sanity check. Gamma AB NB, what is that? Well, that is GAB NB plus epsilon NA NB, right? And now what is that? Well, this will just give me NA, correct? Now, and nobody complained that I forgot the NB here. Nobody was paying attention. Well, great. No, I'm kidding. So now what does NB give me? That is? No, it's minus epsilon, exactly. So this is minus epsilon. So these two epsilons will give me a plus 1. So this will give me minus NA. NA minus NA is also known as 0, right? So that is 0 as we want it to be, right? That's wonderful. That means we're still on track. We still understand what's going on here. Okay. So now the next thing we can do is we can define a covariant derivative on our induced slices, in this fluoration, on the slices. Okay. How do we do that? Well, we call it the spatial covariant derivative. Okay, and how do we define that? We define it by completely projecting every single index of our covariant derivative in the space-time onto the slice. Okay, so for example, if I denote that covariant derivative with a D now. Okay, so D will be the covariant derivative that is associated with our spatial metric gamma. Okay, look at the sheet that I handed out yesterday with the convention. Okay, that's our covariant derivative associated with gamma. If I take the derivative of the covariant derivative of a tensor TBC, for example, then what I'm supposed to do is project every one of these indices into the slice. So I need 3 gammas now, right? There will be 1 gamma for A, gamma AD, say. Then I have a gamma for the index B, okay? So that I need a B upstairs, and then I have an E downstairs, say. Then I need another gamma C for the index C. CF, and now I'm running out of space. Maybe I should erase a little bit more here. And now I have a gamma F, and now I take the covariant derivative in the space EF. Okay, so that's how I define this. All right. By definition, this is a tensor because all of these objects are tensors. Okay. Also, by definition, it's spatial, because we're projecting everything into the slice. So we already know this is a spatial tensor. That's what we want. For this to be a well-behaved covariant derivative, we also want it to be compatible with a spatial metric. And I'll ask you to show that today in the afternoon in the tutorial. Okay, so what we write down for now is that this is a spatial tensor. It is also compatible with gamma AB. And what I mean by that is that if I take the spatial derivative of the spatial metric, I automatically get 0. Okay? And again, we'll work on that this afternoon in the tutorial. Okay? So that means this has all the properties that I'm looking for in the covariant derivative, and we can move on. Now, where do we want to go? Well, ultimately, we want to project Einstein's equations on these slices. So we need not only the first covariant derivative, but actually we're working towards the Riemann tensor, right? The Riemann tensor has second derivatives. So basically, we want the second covariant derivatives of tensors, okay? But before we do that, we already mentioned the word Riemann tensor. So how do we define now the Riemann tensor on this slice? Well, we do it in exactly the same way as in the four-dimensional space. We say, well, we define it in terms of the commutator of the second derivatives of a vector, okay? So we define the 3D Riemann tensor as this. We now have the spatial covariant derivatives, dA, dB, of our vector VC, minus, now the commutator, so I flip the A's and the B's, so this gives me a dB, dA, VC. This is R, D, C, BA, VD. This is how we define this. Now our spatial Riemann tensor. You will note with great relief that there's no 4 hanging around there anymore. We were getting tired of writing that out anyway, okay? So this undecorated R is now the Riemann tensor associated with our spatial metric, okay? Now this holds for any spatial vector VD, okay? But what that means is it still leaves undefined the time component of D, because VD is spatial, okay? So we need to do one more thing to actually make this well defined for the time component of this. So we need to add one more condition, and we'll say that if RDCBA times ND, here's our normal component, that be 0, okay? So this jointly now defines this tensor, and this holds for any spatial VD, okay? Yes? Okay, so this basically, we define the Riemann tensor in this way for any spatial vector V, okay? But what you notice is that basically this then only covers the spatial components of D, okay? That means it leaves the normal component undefined. And so to define that, I add this definition to make clear that this is now a completely spatial tensor, okay? All right, actually let's take stock of where do we stand. Basically what we've done is we've decomposed tensors into spatial and normal parts. We've introduced the covariant derivative on our hypersurfaces, all that is fine. Ultimately what we want to do though is we don't want to do more than this. We want to decompose not only tensors, but actually we want to decompose Einstein's equations. We want Einstein's equations are defined in our space-time, but we want to decompose the equations that either hold on these slices or tell us how to move quantities forward from one slice to the next, okay? Now, Einstein's equations contain the Ricci tensor, which is really, it's a trace of the Riemann tensor, so we're dealing with a 4-dimensional Riemann tensor in Einstein's equations. We've now defined the 3-dimensional Riemann tensor in Einstein's equations. So that means we're on good track here. We can now compare these two, okay? But what you notice is, if you think about it, this cannot be all. This cannot be the end of the story, because the spatial Riemann tensor only contains spatial derivatives, but the 4-dimensional Riemann tensor also must contain time derivatives. So we must introduce a new tool to capture the time derivatives of things, okay? And that leads us to the notion of the extrinsic curvature, okay? So basically, the gamma ij, the spatial metric, that tells us about the curvature that is intrinsic to every slice that we're introducing. But now those slices can also be bent, or you know, they can be curved in fancy ways as they are embedded in this higher space, okay? And we want to capture that curvature, you know, that is a result of this bending of the slices in these higher curves. And that's what we will describe that with the extrinsic curvature, okay? So let's introduce the extrinsic curvature, as opposed to the intrinsic curvature, okay? So sometimes we call the induced metric gamma the intrinsic curvature, and then to highlight the difference from the extrinsic curvature, Mathematicians also sometimes call this the first and the second fundamental forms. Okay? So we'll call it the extrinsic curvature. Okay? And here's a picture. Imagine maybe here's our slice. Okay, maybe these are coordinate lines on the slice, and this is kind of curved in our space. Maybe here's our spacetime M. This is some slice sigma. Now, how can we measure how this is bent? Well, this is how we can do it. We can consider how normal vectors change. Here's one normal vector A. Okay, it's normal on the slice. If I move over a little bit, we'll notice that the normal vector now points in a different direction. Here it is. Okay? Okay? So if I had just moved this one over, then I would have gotten, this is a copy of this normal vector. Okay? And we notice that the direction of the normal vector changes as I move around on the surface. Okay? So this suggests that I can measure the curvature by figuring out how much does the normal vector change. Okay? How do we measure changes? Well, with covariant derivatives. Now, the normal vector is a 4D object. It lives in the spacetime, so we'll use the 4D covariant derivative. Okay? But then we want a spatial tensor from that, so we will take the four-dimensional covariant derivative of the normal vector, but then we'll project it into the slice, and that is the extrinsic curvature. Okay? So we project the gradient of NA into sigma, and that gives us the definition of the extrinsic curvature, which we denote KAB, and it's defined by convention. I'll use the minus here. Don't complain to me. This is just convention. Okay? We project this into the slice, so we need two copies of gamma because they're two indices, gamma AC, gamma BD, and now the covariant derivative of N. Nabla C and D, right? That's exactly what I advertised. So this is the extrinsic curvature. Okay? One thing that is not exactly obvious is that this is actually automatically covariant. That arises because of our definition of N. I will not prove that. I'll just tell you this, that this is automatically symmetric. Okay? All right? What should we do next? We should go back to our example of the sphere embedded in flat space and figure out what is the extrinsic curvature of the... Oh, you had a question? Yes. You know, I apologize. I really have a hard time with the noise outside my friends. Yeah? Yeah?
And then we are taking into account how it curves, every splice curve.
Yes.
What if right from the start, we do splicing in different fashion for the whole space time? Like at certain point of time, now what we do is we are taking the NA in the time direction. And right from the start, we do splicing differently. Like a particular section of this space time that you can see, which is curved in a certain fashion, you can take one slice with NA.
Yes.
And then NB, then NC, then NB.
Yes. So, I mean, so far I've not restricted this in any way. I just said basically we'll take any slice, okay? I've not told you anything about how I've picked these slices, right? So this is completely general. Also, remember I told you that we'll introduce these slices as level surface of this function t. But this t is also still completely general, okay? It could be any function. So basically you can choose any slice that you want as long as they're not intersecting, you know, and it's...
My question was, the splicing remains consistent for the whole space-time.
Okay.
The splicing itself changes as the time goes.
Okay, so the slicing changes.
The slicing changes over the space. If that way we
Well, okay, so... Okay, I think you're asking, are we assured that we can do this globally? Is that what you're wondering? And, you know, I would like to stay away from those questions. So basically that depends on how exactly you choose your slicing, and do these slices exist globally? I would like to stay away from that. So what I'm saying is, at least locally, we can do this, okay? And then we'll worry about everything else later. How's that? Okay? Okay, let's go back to our example though, where we embedded these spheres in a flat spacetime, and let's work out what is the extrinsic curvature of these spheres. Okay? All right. So back to our example. And now we work out the extrinsic curvature. Okay? To do that, I first need to work out what is... We already know what the gradient is, what the normal vector n is, right? Now we need to work out what is this covariant derivative. Let's do that. Okay, we have nabla A and B equals partial A and B. What is going to happen to these terms? They are all 0 because the only non-zero component of n of the normal vector was 1. When we take a derivative of 1, it will be pretty 0, right? So, but will this whole thing be 0? No, because it's a covariant derivative, so we need to take into account the Christoffel terms. So there will be an NC. And you know what? I'll use a little 3 here to remind us that now we take the covariant derivative of the embedding space. Okay? So these are now the Christoffel symbols that are associated with our 3-dimensional, the embedding space. Okay? Now, aren't we lucky that we just worked out these things yesterday in the tutorial? Okay? As if somebody had some foresight as what is going to happen, right? So now the only term that we need is the radial component. So this is the same as minus the radial component is 1. So this is our 3 gamma r a b. So now we look these up. Okay, they're right. Now the other thing is, in a minute we'll project this onto our sphere, right? Because we need to take these to account. But we remember that the gammas, they only now have theta and phi components. The only theta and phi components of these terms, turns out we can write exactly as the metric. So you can check that this is exactly 1 over r gamma AB, where gamma is now the induced metric on the sphere. Okay? So that means, basically, and now you can, did I forget a minus there? No, that's correct. Okay? So you can check, okay, that this is true. And what we find is that the extrinsic curvature equals minus 1 over r times gamma AB. Okay? All right? That's the extrinsic curvature on these spheres. Now this gives us a little bit of a hint. Remember yesterday I pointed out the following too. If we look at the Riemann tensor of the embedding space, it was, did I hear 0? Unfortunately I didn't, but it's 0. The embedding space of this, in this example, it's flat space, so the Riemann tensor is 0, right? We found yesterday in the tutorial that the Riemann tensor of the sphere is non-zero in this puzzle. How can that be? Okay, the embedding space has 0 curvature, but now we have this curvature. Well, here's a hint that the Riemann tensor of the sphere only gives us the intrinsic curvature. This is the extrinsic curvature. It's possible that in some way, we need to take into account both the intrinsic and the extrinsic curvature together to get the curvature of the embedding space. Okay, and that's exactly what we'll work out in detail. We will derive that. Okay, but that gives you a hint. That's where we're headed. Okay, okay. Now we're back to the extrinsic curvature. Later on, I'll refer to this definition as our form 1 of the extrinsic curvature. That suggests that we'll write down different forms, different expressions for the extrinsic curvature. Okay? To derive our form 2, I'll first define the acceleration of a normal vector. Okay? So we define the acceleration of a normal vector, of this, of normal observer. And that is the following. A, basically we define this exactly the same way. You know, you've probably in a general relativity course, you know, you've learned how to define the acceleration of an observer with a forward velocity u. It's u dotted into the covariant derivative of u. And we'll do the same thing here. We just replace u with n. And then we get nb, nabla b, na. Okay, so this is the acceleration of a normal observer. By the way, what happens if I interchange these two indices? Okay. Note. What is this? It is exactly 0. Why is that 0? Exactly. I can take the derivative of that minus the other one, but that's because of the normalization. That is 0. Okay. If that's not clear to you, work it out as a little exercise. All right? Okay. Then I can do the following. Okay. Remember this. We'll use this a fair bit. Okay. This property. Okay. Then let's write this KAB in a different way. Let's write it this way. We have KAB. We've said that this is that. Okay, but now let me insert the definition of the spatial metric. Then I get minus GAC plus epsilon NA NC times GBD plus epsilon NB ND times gamma C, delta C ND. Okay? What happens with this term if I have this term act on that? Do we all agree it's 0? It's because of the ND, nabla C, ND. That's exactly this term. That is going to disappear, right? So this term is gone. We like it when that happens, right? Okay, so now we only have this term left. So this is the same. And now from this term we just have a G, BD, but that's like a delta, right? So basically that means we can now replace one of the D's with a B. So that means what we have left over is minus G, AC plus epsilon NA NC times nabla C NB. Okay? Now what is this? Well, the first term is again just a nabla operator. So this gives me minus nabla A and B. And then the second term gives me, what does that give me? Well, now we discover that NC, nabla C NB, that's just the acceleration, right? So this is minus epsilon NA AB. Okay, you agree? So let's put a box around this. This is our form 2 of the eccentric curvature. Basically what we've done, you see this term is almost exactly the same term like this, except we have not projected it into the slice. Okay, so this term still has a normal component, but that normal component is now being killed off by this term. Okay? Now one more comment. I told you that this is exactly symmetric. If the left-hand side is symmetric, the right-hand side better be symmetric too. So that means that I can also write this as minus nabla A and B with the parentheses that give me symmetrization, minus epsilon N A B. Okay, that's the same thing. All right? Okay. Now, yes? That made a B out of the D. Right? Okay. There's another interpretation of the eccentric curvature, and that is an interpretation. Actually, at what time did we start?
At 10 o'clock.
At 10 o'clock. Then tell you what, why don't we take 2 minutes break now? But let's really keep it to 2 minutes because we started late. So let's not delay it too long. And there's lots of stuff that I want to talk about. So let's just have 2 minutes, but maybe we can all get up and rest and wake up again. Okay. I guess everybody who's here will say, yes, we are ready, but of course those who are not here yet don't have a chance to say no, which is great. Let's get started. Okay. So so basically, I told you about two forms for the extrinsic curvature. There's really the physical interpretation of the extrinsic curvature. It's related to the time derivative of the induced metric. Okay, but to see that, we actually need to talk about the Lie derivative of this metric, and that introduces the Lie derivative. So my next question is, who of you has already been introduced? Who is an old friend of the Lie derivative? Let's put it that way. Has anybody seen the Lie derivative? Okay. A few. Okay, so, but it seems like it's a good idea to maybe talk about the Lie derivative briefly. Okay, so let's do a little interlude. Okay, so, and let's talk about the Lie derivative. Here's the point. Imagine we have some manifold, we have some space of some sort. In this space, we have a vector field. Maybe I'll call these vectors XA. And these vector fields now also introduce the notion of integral curves, so I can introduce some curves that are the integral curves of these fields. So these are integral curves, okay, so which are parameterized by lambda in such a way that dx, d lambda, if I take the derivative of these curves at each point, i.e. if I compute the tangent on these curves, then the tangents are always exactly equal to the vectors of this vector field. So this is equal to x, this capital XA. Okay. Now, what I'm interested in is how can I define the derivative of some quantity q, which might be a scalar, might be a tensor, whatever it may be, okay, along this vector field. Okay. So let's look at the derivative of a quantity q along XA. Okay? So I'm tempted to do this, the way you define a derivative in a math course, as saying, well, great, we'll look at q at two different points, and we'll compute the difference, and then we'll let the difference go to 0, and in the meantime, we also divide by the distance, right? So it will be something like that. We'll let delta lambda go to 0, and then we look at the difference between q at some point XA, okay, minus the quantity q at XA plus our delta lambda times the vector XA, okay? So basically we have one point XA here, and then another one that's separated by a delta lambda, and then we let that delta lambda go to 0, and what we still need to do is divide it by delta lambda, okay? So far, so good. Okay. What you notice, though, is that we're comparing this quantity q at two different points. Okay. So compare q at two different points. Okay. This is fine for scalars. Okay. And in fact, for scalars, that's exactly how we define this derivative. Okay. So unambiguous. For scalars. Okay. But what happens if we consider higher rank tensors? Rank 1, 2, 3, or whatever. But what about okay? So what we could do, well, why don't we do the easiest thing there is, and that is just compare the coefficients, the components of the tensors. Okay, so we could compare components. Okay, and in fact, that's exactly what you do for the partial derivative. That gives you the partial derivative. But the partial derivative is not a tensor. Okay, and actually, one way how we can think about that from this picture is the following. What happens if I look at a coordinate transformation? Okay? Now, a coordinate transformation may be space dependent. It may be different at different points. So that means if I transform the tensors at these two different points, the transformation may be different. That means that this difference will be different, and it's evident that the result cannot be a tensor because it doesn't transform in the right way, okay? Because we're comparing things that are being transformed differently. So that means that this is a no-no. We should not be doing this, okay? It does not give us a tensor, okay? Okay, I should write down. This cannot be tensorial, okay? But what this also tells us is here's how we can fix this situation. What we need to do is we need to obtain a covariant, a derivative that is a tensor. We need to compare these two objects at the same place. So instead of comparing them here and here, we first need to drag the tensor from one place to the other so that we're actually comparing the two objects at the same place. Okay? So we learned from this that we need to compare tensors at the same point. Okay, so that means we want to drag a tensor, t from a point P, okay, which so maybe I call this point P, okay, and I think oh, this is too bad. So this is a quantity Q, and now I realize I named the P, this point also Q. So there are two people called Q right now. Do you think we can distinguish them? Anyway, so okay, so we're dragging this tensor T from a point Q, P, which is at XA, to another point Q, which is XA plus delta lambda times capital XA. Okay, so the picture is this. Here's our line, the integral curve of this vector field XA, here at P, here's XA at Q. Okay. Now here's a tensor T, okay, which lives at P. Here's a tensor T, which lives at Q. But instead of comparing these tensors at these different points, we now want to drag this tensor P to Q. Okay, and so this is a version of our tensor P that we've dragged over there. Okay, and this is now, and maybe I'll now call that T prime. But this is basically the dragged tensor T at P, which we've dragged over to Q. Okay, so we need to do this before we compare the two of them. Is that roughly clear what I'm doing here? I'm just saying that basically we cannot compare the two tensors at the 2 points. Therefore, we need to move one tensor to the other point, okay? And then we can compare them. They will still be different in some ways. The immediate question that this should raise is, but wait, you talk about dragging the tensor, but how do you suggest we drag the tensor? Okay, how do we do that? Well, there are two different ways, or maybe even more than two. There are two that come to my mind, okay? Actually, do you have a suggestion what we should do? Excellent. So you're already thinking about the Lie derivative. Okay. You could also think about, well, we've talked about parallel transport. Why not using parallel transport? Instead, for the Lie derivative, we're not going to do that. We'll use an infinitesimal coordinate transformation, okay, to move this tensor over there, and that gives us the Lie derivative. All right. So let me write that down. Yeah, okay, so this is how we do this, okay? Consider an infinitesimal coordinate transformation. Okay, so we say, well, our XA prime, okay, is our old XA, right? So basically the new coordinate location over here, which is XA prime, is the old XA. Okay, that plus a delta lambda capital XA, the vector field, so that brings us in that direction, right? So now, how do we compute a coordinate transformation from that? Well, basically, we want a coordinate on my sheet that I handed out on tensors. I introduced this coordinate transformation matrix A prime B, okay, which is just partial xa prime, partial xb. And now we see if we insert this to first order, okay, we get delta a prime b plus delta lambda partial xa partial xb, okay? And this is to first order, okay? And which is all we need, because then we take the limit, all right? And then basically you work out, you drag these tensors over there. I suggest actually we don't do the details because we have many other things to talk about. But basically, this is the essence of the Lie derivative. And what we obtain then is the following, okay? Okay, so then we get the Lie derivative. So for example, of a mixed rank 2 tensor, okay, we write the Lie derivative as this funky L, okay, with the vector x that we're dragging along. Yes?
Delta will be not A prime, just
You're right. Well observed, okay? Basically, you would think there should just be an A, okay? But in fact, it doesn't matter because the difference is higher order, okay? So, okay, you know what? You choose. That's a higher order effect because the difference is in delta lambda, so it doesn't matter, okay? Okay, so now we have the Lie derivative of x of t a b. We define that as the limit of delta lambda going to 0 of t a b, which we've t a b, which lives at x prime. The minus that's minus the drag version at x prime, so we're comparing them at the same place, divided by delta lambda, okay? And so what does the Lie derivative do? Well, it is 0 if, in fact, the only difference between these vectors are those that arise from an infinitesimal coordinate transformation, right? That means that a non-zero Lie derivative measures a deviation from an infinitesimal coordinate transformation. So that's what a Lie derivative does. It measures differences, or a deviation from a mere coordinate transformation. Okay, so this is the difference between the Lie derivative and the covariant derivative. The covariant derivative measures deviations from parallel transport. The Lie derivative measures deviation from an infinitesimal coordinate transformation.
So
Yeah.
the covariant derivative basically measures the curvature of space when we're parallelly transporting.
That's right. So the covariant derivative measures deviation from parallel transport. Okay.
And this Lie derivative measures the deviation.
It measures deviations from just a coordinate transformation.
Okay, so if we have like x, y, z, like some from one coordinate system we move to another coordinate system, it just gives you what is it?
Well, think about it this way. Basically, as I'm going from one point to the other, the coordinate system may have changed and evolved. That means that the vector, the tensor now looks different. Okay, now I could measure, well, is that difference in the appearance of the tensor, is that a real difference, or is it just an effect of the changing coordinate system? That's what the Lie derivative tells you. If the Lie derivative is 0, then that tells you there's no change in the tensor. It's just a change that is due to the coordinate system. All right? Okay, so now we can insert these expressions for these tensors. And again, I'm not going to do this in detail, okay? But I happen to know a book where you could read up on that, for example, okay? But then you could, what we find is following, for example, this, okay? So for this mixed rank tensor, the Lie derivative along x is one term that is basically the advective derivative along x of this tensor, partial c t a b, and then we get additional terms for each index. We get them with a minus sign for an upper index. So now for the a part of, oh, did nobody notice that I forgot the TAB is, okay, there we go. Okay, so for the A, we get CB, now a partial CXA, And now with the plus part for the lower index, that will give me a T, A, C, partial C, X, A. No, that's partial B. Okay? That is the leader of a mixed tensor index. In the tutorial this afternoon, I'll ask you to show that in fact, because of the appearance of these different terms, I can replace all the partial derivatives with a covariant derivative. Okay? So this is in fact the same. Oh, yes. Okay. This should be a C. Exactly. Thank you. Yes. Okay, so now I can replace all the partial derivatives with covariant derivatives. So this would be AB minus TCB CXA plus TAC nabla, C. All right? And in fact, this is true for any symmetric connection. Okay, you can do this for any symmetric connection. This will work out. Okay, so you work on that this afternoon. Let's do an example. Okay, we introduced the remember, we're coming back to the extended curvature. I told you that the extended curvature is something like the time derivative of the metric. Yes?
If we are replacing the partial derivative with a covariant derivative, I mean, what does that say about the space?
That you don't need, you need very little structure. You don't need to know about the covariant derivatives because you can just do it in terms of partial derivatives. Okay? Okay? But actually, it'll be clear if you do this exercise this afternoon. It'll see how that works. It'll show how that works. Okay. Okay. So let's. Yes, I said that the extended curvature is like the. Everything okay? Okay. It's like a time derivative of the metric. I didn't tell you what I mean by the time derivative. Because, in fact, we haven't really introduced the time yet, but we have a normal vector. So why don't we work out what is the Lie derivative of the spatial metric along the normal vector? So let's do this as an example. What is the Lie derivative along the normal vector n of our spatial metric AB? Well, I'll use this expression, except now I have two lower indices, so that means I get two terms with a plus sign, and then I have this. From our definition of the Lie derivative, I can write this. I'll use actually the covariant derivative as NC nabla C of gamma AB. That's the first term, this advective term. And get two more terms, one for each index. I have a gamma CB nabla A and C plus gamma AC nabla B and C. All right? Now let me do the following. Let me replace gamma with the definition in terms of the space-time metric in n. So I'll write this as NC nabla C of GAB plus epsilon NA and B plus, and now I get two more. I get a GCB plus epsilon NC and B times nabla A and C, and another term which is, well, maybe I'll just write it out. GAC plus epsilon and A and C times nabla B and C. All right? Nothing magic has happened. I just inserted the definition of gamma. Now, let's look at these terms. What happens to this first term? It is 0. Why is it 0? Covariant derivative of the metric. It's done, right? What happens to this term? Why is that 0? Because of the NCs. Isn't this lovely how this happens? Right. So what happens with this term? Okay. Of course, what you learn from this, whenever you ask what is this term, the safe answer is 0, right? Okay, so now what do we have here? Now here we have, what do we have left over? We have an epsilon, and okay, and now let's see, what do I have? I get two terms. I can operate with this okay, this is just a leader for basically for an upstairs index you need a minus, for the downstairs index is a plus. That's just the way it works out. Okay. Whereas now we have two downstairs indices, so that's why we only have pluses. Okay. Okay, so now we have two terms. I get one term that is, if I act on the NB, then I can pull out the NA. So I have an NA, NC, nabla C, NB, right? Then I have an epsilon NB, NC, nabla C, NA. You believe that? Okay, I don't hear any protests, okay? Then here I only have left over the GCB, but this is a metric that commutes. I can pull that into the covariant derivative and then use it to lower the index in the C. So all I have left over from this one is an nabla A and B. I can do the same thing here. That gives me a nabla B and A. You with me? Okay. Now, what do we have from this? Now, what is this term? It is the acceleration. This is AB, and this term is AA, right? Now, this is starting to look awfully familiar because that looks like our form 2 of our extended curvature. In particular, once I realize, oh, these two terms are different only in the position of the A and B, but they commute. So I can write this as the following. I get 2 times nabla A and B plus epsilon N A B. Okay, and this you recognize as what I called form 2 of the extended curvature. So that means we can replace this with KAB, and we realize that KAB is directly related to the Lie derivative of the spatial metric along n. Okay, so this, what we've derived is this. We have KAB equals minus 1/2 times the Lie derivative of n gamma AB. Okay, and this is what I'll call form 3 of the extended curvature. Okay, this, if you want, motivates our interpretation of the extended curvature as a time derivative of the metric, the spatial metric. All right. Okay, let's go. Yes, very good. Okay, now we are ready to come back to our storyline, right? The storyline was this. We want to decompose Einstein's equations. Okay, the Einstein's equations ultimately contain the Riemann tensor. Okay, we'll use that as a connecting point. So why don't we do the obvious, and that is we'll decompose the Riemann tensor into spatial and normal parts. Now, earlier today, I showed you if you have more than one index, there will be mixed parts as well. The Riemann tensor has 4 indices, so we expect some pain now, right? We need to project 4 different indices. So let's do this, okay? So let's talk about the decomposition of the Riemann tensor. Okay? And we expect that we decompose the space-time Riemann tensor. We expect the spatial Riemann tensor to play a role, but we also expect the extended curvature to play a role, as I motivated before, because that will accommodate the time derivatives of the metric. Okay? So let's start. Let's consider the 4-dimensional Riemann tensor. So here's our 4 again to distinguish it from the spatial Riemann tensor. 4 are A, B, C, D. Well, that's the same as G, A, P, G, B, Q, G, C, R, G, D, S times the same thing, 4 R, P, Q, R, S. So far I've only introduced gammas, but now I'll replace each G with a gamma AB plus epsilon NA NB, right? So this will be the same as gamma AP minus epsilon NA NP. And now guess what? We have to write this for every one of these, but I'm getting tired, so I'll just write, you know what's in there, okay? And then we still have this term, R, P, Q, R, S, okay? And now maybe I'll continue this equation over there. Okay, so what do we get? Well, the first term that we get is we pick up the gamma from each one of these, and that gives us a purely spatial projection, right? Good. So that will be gamma AP, gamma BQ, gamma CR, gamma DS times R, PQ, RS, and this is purely spatial. Right? What is the next term? The next term will be one for which I pick 3 of the gammas, okay? But one normal term from each one. There will be 4 of these terms, okay? Basically, because I have these 4 different combinations. So these will be terms of the type epsilon gamma AP, gamma BQ, gamma CR, AD, and S times 4 RP, QRS, and there will be other terms of the same 4 depending on which n terms I pick, okay? There should be, yes, I think you're right. There should be a minus. That's right. Okay? These will be, so these are the terms that have 3 spatial projections, 1 normal projection, okay? So one index, if you want, is normally projected, okay? You think, oh my goodness, we have a lot of work ahead of us, right? But let's see what happens. So the next type of terms that we get is 2 gammas, 2 n's, okay? So we have terms of the type, and now that both the plus and the epsilon cancel, the minus and the epsilons cancel, so we now have gamma AP, gamma BQ, NC, NR, ND, and S times 4 R, P, Q, R, S. And other terms that are similar, so these are the ones with 2 indices. Normal. What is the next term? So I just told you, whenever I ask you what happens with this term, the correct answer is? It's 0. Why is it 0? What happens if we have, now the next one would be 3 normal vectors, right? So if we contract this with 3 normal vectors, why is that 0? Because of the symmetries, right? Then the normal vectors will be symmetric, but any pair is antisymmetric. So that must be 0. So this is some good news, okay? We just saved a lot of work. Okay, so it's projection. There are only 3 different types of projections of the Riemann tensor. Purely spatial, 1 index normal, 2 indices normal. That's all we have, okay? Okay, so let's write that down. So there are 3, so done, right? There is no more to be done. So we have 3 different projections. And that means we should expect 3 different types of equations, okay? We expect 3 different relations, 1 for each one of these, okay? So we expect 3 different equations that relate the 4-dimensional Ricci tensor to 3D quantities. In particular, the 3-dimensional Ricci tensor, okay, R, A, B, C, D, and the extrinsic curvature KAB. Okay? So we have 3 equations. We expect that we will have 3 equations. Interesting spelling of equations, by the way, there. Okay? And in fact, those 3 equations are the equations of Gauss, Codazzi, and Ricci. Okay? Okay, so that's what we'll find. The Gauss equation we will actually derive explicitly. Okay? These will derive hand-wavingly because it's just more of the same kind of math, and we'll just use the result. Okay? But actually, the Gauss equation we should derive. Okay? Now, to get started, what do we? Yeah, and I think we'll have time to get started on that. To get started, what do we want to do? Well, we want to relate Riemann tensors. Okay? we want to relate the 4-dimensional Riemann tensor to the 3-dimensional Riemann tensor. The Riemann tensors are expressed in terms of second derivatives of a vector, right? The second covariant derivatives of the vector and really the commutator. So what we'll do is we'll first start work a little bit more on these derivatives of vectors and see what form we can bring them in, okay? So this is just some groundwork to prepare the derivation of these equations, okay? So let's look at the first derivative of a vector, okay? So let's say dA VB, okay? This is gamma A C gamma B D times nabla C VD. Right, by definition, that's how I defined the covariant derivative of a vector, okay? This way. Now, let's rewrite this a little bit in a way that will be useful later on. And to do that, I will again express the spatial metric as G's and N's. So this was the same as gamma AC times G BD plus epsilon NB ND times nabla C VD. Okay? Okay. What I should say of a spatial vector VD. Okay, so we're only interested in spatial vectors. If VD is spatial, then its dot product with the normal vector n is 0. But we see there's an nd here, so there's a dot product here. Since this dot product is 0, I can actually flip the two for the price of a minus sign, right? Okay, so this is the same as gamma AC times, and now let's see what happens to the first term. So for the second term, we'll do this trick. For the first term, you just see, oh, this is the covariant, this is the metric. I can pull that in here, and then I get nabla C VB, right? So this, again, flipped, made it a B out of the D. For the second term, I now have a negative sign because I'll flip these two arguments, and then I have a minus epsilon. I have a gamma AC times an NB, but now I pull the VD out, and I have left over nabla C ND. Right? You with me? No, actually, I'll continue this over here. Now, because VD is a spatial vector, I can write VD as a gamma D E VE, okay? So I can introduce another gamma if I want to, and then what I get is the following. The first term is just gamma AC nabla C VB as before, but now I can write this as epsilon, minus epsilon NB, and now I write this as a VE, okay? Is this E, okay, and now I have two gammas. I have a gamma AC and a gamma ED, and now I have a V nabla C ND. You believe that? Does this combination look familiar? That's the correct answer. Yes, it better because what is it? It's the extrinsic curvature, right? Strictly speaking, minus the extrinsic curvature, and it's minus K AE, okay? So then this whole thing is gamma AC nabla C VB plus epsilon, okay, because of the minus, plus epsilon K AE NB VE. Okay, so this is what have we done? Well, effectively we've expressed the spatial covariant derivative of V, okay, which is defined with two gammas. Basically, I saved you one gamma because now there's only one gamma left, but the price that we're paying is this extra term, which is an extrinsic curvature. Okay? Right? What I'll ask you to prove on the tutorial this afternoon is the following. Okay? So you will show that if I look at second derivatives, dA dB, okay, VC, which we haven't talked about yet. We've defined the first covariant derivative. Okay? We haven't defined the second covariant derivative, but of course you do it as the first derivative of a spatial tensor, except that the spatial tensor happens to be the first derivative of a tensor. Okay? So you look at this and you'll prove that this is the same as gamma A, P, gamma B, Q, gamma CR times nabla P, nabla Q, VR. You might have expected a term like that, which is a spatial projection of the second derivative, but because really this is a second derivative, not just the first derivative. For the first derivative, we would be done, right? But now it is the second derivative, so the extra terms, two of them. One is minus epsilon K AB gamma CR NQ nabla Q VR, and then it's a minus epsilon K AC K BQ I'm sorry, BP times VP. Okay? So basically, how do you derive that? Well, you think about how you define this object, then you use manipulations very similar to what we did here, and by the end of the afternoon, this is what you'll get. All right? Did I make a mistake? Or any question? No. Okay. I actually think that this is a very good place to stop. Okay. So that's it for today. I'll see you in the afternoon, and then we'll work out some of the details that we've discussed today. All right? Thank you.